We're now going to look at the construction of titration curves, and we're going to start with strong acid, strong base titration curves. So the way the pH changes with volume during titration is the titration curve, and it depends on the type of acid or base that is reacting. It is important to understand this, as a pH change at the equivalence point must be used to choose the appropriate indicator. Now, when we're thinking about constructing titration curves, the pH, we have to consider a couple of things. The pH in the titration flask is going to be changing as the titrant is added. The pH in the flask can be monitored with a pH electrode, and this pH can be plotted against titrant volume to obtain the titration curve. The equivalence point in the titration can be determined and used to find the concentration of the titrant. So if your titrant is unknown, is of unknown concentration, this information can be used to find the concentration of the titrant once the concentration of the titrant is known. And as we mentioned before, the titrant is normally a standard solution. The pH at the equivalence point can inform you as to which indicator can be used to identify the endpoint. If the correct indicator is used, it will be a good estimate of the equivalence point. So let's look at an example of a strong acid, strong base titration curve. So there are a couple of things that we should notice here. So in this case, your sodium hydroxide would be the titrant because it's being added as the reaction goes along. And we see that the pH starts out low when there is no titrant added. The pH starts off low, and our titrant in this case would be hydrochloric acid. As we add titrant, as we add sodium hydroxide, we see an increase in the pH until we get to the equivalence point. We see that there's a sharp change in the pH at the equivalence point, and then the pH increases slowly again and then levels off here. The different indicators are shown, two possibilities, phenolphthalein here or methyl red. Okay, so this is an example of a strong acid, strong base titration curve, and we're going to discuss it just a little bit more. Okay, so for strong acid versus strong base titration curves, we will calculate the pH at 4 points in the titration curve. Before any titrant is added, after titrant is added, but before we get to the equivalence point, at the equivalence point, and then beyond the equivalence point. So we're going to examine the titration curves at these points. So let us look at some considerations for strong acid, strong base titrations. So the pH of the solution in the titration flask will depend, as we've said, on the concentrations of the acidic and basic species in the solution. If the titrant, the species in the flask, is an acid, then the initial pH will be less than 7. If the titrant is a base, then the initial pH will be greater than 7. Before any titrant has been added, if the acid is a strong monoprotic acid, then the concentration of the protons will be equal to the concentration of the acid. And if it's a strong monobasic hydroxide, then the concentration of hydroxide ions will be equal to the concentration of the base. Now, in the example we're going to look at in a second, the strong base is the titrant. So it's a species being added from the burette. All right. So in this example, we are titrating 25 centimeters cubed of 0.113 mole per dm cubed HCl with 0.097 mole per dm cubed sodium hydroxide. So we have a strong acid and a strong base. So some things to consider. The initial volume in the flask will be the volume of acid, which would be your 25 centimeter cubed. We are going to be looking at the volume of our titrant that is being added, and we have to consider the molarity of the acid and the molarity of the base. So in this case, we know the concentrations of our acid and base. In other cases, we may need, in the lab, for example, we may need to determine the concentration of an unknown. So first thing we have to consider, what is the pH before any base has been added? Because HCl is monoprotic, a strong monoprotic acid, the hydronium ion concentration is going to be equal to the concentration of the acid. And so finding the pH is fairly simple. Minus log of the hydronium ion concentration. Right? Good. So I want you to consider what would be the hydronium ion concentration if the strong acid was sulfuric acid instead. So think about that carefully. Now, we want to think about, because we know the concentrations of our acid and our base, we can consider calculating the equivalence volume, right? So at what point, at what volume of sodium hydroxide would we expect that all the HCl in the flask would be neutralized? So we write the equation for a titration reaction, sodium hydroxide plus HCl producing sodium chloride plus water. We see that there's a 1-to-1 mole ratio between the acid and the base. We calculate the moles of acid originally in the flask, right? Concentration times the volume in liters, okay? And this tells us the number of moles of acid originally in the flask. Because there's a 1-to-1 mole ratio between them, we expect that the same number of moles of sodium hydroxide would be required to neutralize the HCl. So from this, we can find out what volume of base would be required. So we know the concentration of the base. We're trying to figure out what volume would be necessary to neutralize the acid, and we already know how many moles, right? So we transpose that same equation that we used earlier to find the equivalence volume. And this tells us that in order to neutralize our HCl, we will need 29.12 centimeters cubed of 0.097 moles per dm cubed sodium hydroxide. All right. So let's examine a pH before the equivalence point. So we've looked at what the pH was initially. It was 0.95, right? So it's expected. We have a strong acid, the pH is going to be low. We have an idea now what the equivalence volume would be, and now we're going to examine a pH before we get to the equivalence point. So again, we have the titration reaction there. And we want to calculate the pH after we've added just 5 centimeters cubed of our base. So again, we saw that the initial moles of acid that we had in the flask was the concentration times the volume in liters to give us 2.83 times 10 to the minus 3 moles. And in this case, we're saying that we've added 5 centimeters cubed of base. So we can determine the moles of base that have been added by multiplying the concentration of your base times the volume in liters that has been added. So if we only add 4.85 times 10 to the minus 4 moles of base, we can only neutralize that number of moles of our acid, which means that we are going to have some of our acid left over in the flask. So we have neutralized a portion of the acid and we have some that will be remaining. So to find the amount of acid, the number of moles remaining, we subtract the initial moles of acid, well, subtract the moles of acid neutralized from the initial moles of acid, and this tells us the number of moles of acid remaining in the flask. Now at this point, what is going to be contributing to the pH? The presence of that strong acid, which is completely dissociated. Those hydronium ions that are produced are going to be responsible for that pH, right? At this point in the reaction. So what we need to do, we think about what the volume, total volume in the flask is at this point. Initially it was 25. We've added 5 centimeters cubed of base, so the total volume in the flask is 30. The concentration of acid in the flask is now 2.34 times 10 to the minus 3 moles divided by the volume in liter, the volume of that solution in liters. And this tells us that the concentration of acid is 0.078 moles per dm cubed. And as we said before, because this acid is a strong acid, it is completely dissociated, so the concentration of hydronium ions will be equal to the concentration of acid that is currently present. And so that is used. Minus log of this concentration tells us what the pH is after adding just 5 centimeters cubed of base. All right. So, all right, we're continuing on. So when we are doing our titration curves, if we're doing it in a lab and we're using a pH meter, we would typically find the pH at different volumes, right? When we've added different volumes of our titrant. Now, if we know the concentrations of our acid and base, and we are constructing a titration curve, we would do a similar thing. We would calculate the expected pH values at different volumes to help us determine or to help us see the titration curve. So you'll see all of these dots here represent different volumes at which a pH has been determined. So now let's look at the pH at the equivalence point. So we know what it was initially. We know what it was once we had added 5 cm cubed. Let's look at the pH at the equivalence point. So what happens? Reaction again that takes place as the base is added. We see that HCl is reacting with our sodium hydroxide, producing water and sodium chloride. After we've added the equivalence volume that we determined earlier to be 29.12 centimeter cubed, all of the HCl would have been neutralized, right? So when we added equivalence volume of sodium hydroxide, all HCl would have been neutralized. So in the solution, all we have would be water, sodium ions, chloride ions, right? So your sodium and chloride ions are neutral. So what is really impacting the pH at this point? Just water. So the equilibrium that is present at this equivalence point is just the equilibrium between water molecules, hydronium ions and hydroxide ions in solution. And so of course the equilibrium constant that is related to this would be Kw. And so if we solved for the hydronium ion concentration based on this, it would tell us that your hydronium ion concentration would be 1 times 10 to the minus 7. So pH would be 7, right? So we're using the equilibrium constant for water. Every time we have these two molecules interacting, we're producing one of each ion. So there's equal concentration of hydronium and hydroxide. And so we can rewrite this equation by using hydronium ion concentration squared and solve for the hydronium ion concentration. It tells us that pH is equal to 7. So in your strong acid, strong base titration at the equivalence point, the pH is expected to be 7. right? Good. So what happens now after the equivalence point? So at the equivalence point, we neutralize all of the acid that was originally present in the flask. And now we're thinking, okay, what happens after the equivalence point? What if I add some additional titrant into the flask? What happens? So if the equivalence point is passed, all the acid in the flask has been neutralized, and all I would have would be excess base. So the pH in the flask, when your titrant volume is greater than your equivalent volume, will be due to this excess base that you've added. So for example, if we add 30 cm cubed of base, right? Remember, the equivalence volume was 29.12. So this means that we've added a little additional base. So the volume of your excess base would be 30 minus 29.12, and that tells us we've added an excess of 0.88 centimeters cubed. The number, we can determine the number of moles of excess base by doing concentration times volume in liters again to find the number of moles of excess base. What do we need to do next? We need to figure out the concentration of excess base that is present. So the volume of the solution, the total volume of solution in the flask at this point would be 25, which is the original volume of the acid, plus the 30 of the sodium hydroxide that has been added. So the total volume is 55 centimeters cubed. We can find the concentration of our base, or the hydroxide ions, by dividing the moles by this volume in liters, and this tells us what the concentration of hydroxide ions would be. All right. Now we're looking at hydroxide ions. So it means we have to determine pOH, which would be your minus log of our hydroxide ion concentration, and it tells us pOH is 2.81. What is the relationship between pH and pOH? pH plus pOH equals 14. So therefore, pH will be equal to 14 minus the value of our pOH. So when 30 centimeters cubed of sodium hydroxide would have been added, we would expect the pH to be 11.19 in this example. All right? And of course, we can calculate at different points when the volume of titrant that has been added, 35, 37, 50, and so on, to help us construct the titration curve. Right? So this is what we'd be looking at here. So beyond the equivalence point, this is what we expect to happen in terms of the change in the pH. So just a summary of the strong acid versus strong base titration curve. So when our acid is the titrand, the pH starts out low because it tells us that we have high hydronium ion concentration. The pH gradually increases as the acid is being neutralized by the base, and then we have a sharp rise in the pH at the equivalence point, and the pH at the equivalence point is 7. Beyond that point, we see that the pH continues to increase slowly as more base is being added. Now, if your titrant was instead a strong acid, and your titrand, so your titrand meaning the species that is in your flask was a strong base instead, what would we expect to happen? The pH in the flask would initially be high, right? And we see here that the shape of the curve is actually reversed. So the shape of the curve is reversed for your strong acid versus strong base, and strong base versus strong acid titration. So the pH starts out high because we have high hydroxide concentration. The pH gradually decreases as base becomes neutralized by the added acid. And then we have that sharp decrease in the pH At the equivalence point, again, pH 7, and then beyond that, we see that the pH decreases slowly. And remember, one of the things I mentioned before was that we have a sharper change in pH at the endpoint when we have higher concentrations. So this is an example. So this schematic just compares the titration curve with two different concentrations of sodium hydroxide, where solution A would be a greater concentration.